talk about various incidents that had happened, and then what is the dynamics of the emergency that you generally face, because we really don't want to get into those kind of things which I'm going to tell you now. At the heart of any emergency, what it takes for that emergency, this is what I'm going to discuss. And I'll also discuss how we verify these things through various mechanisms by creating digital replicas of those things, and then at the end of the day, we tend to make the system safer. So let's start with the past incidents that happened, and then the dynamics of an emergency event, how human behaves in that, what we have learned so far, and of course, I'm very sure that we haven't learned everything yet. We are still learning. So you can see I'll focus on these 5 incidents, and in these incidents you'll see that a very small incident which would otherwise would have been a minor accident and would not be of any value or impact has killed almost as large as 265 people, and in some cases 150 people. These are just international metros from where we have actually heard this, and we have the data. King's Cross, Baku, Azerbaijan, and in some places like Ligau, these are the places where mostly a very small incident turned up to be the worst disaster. And therefore, what we learned out of it is, which is very important now, is this, that whenever a disaster happens, there is a series of events that actually lead to that disaster. There's a series of mismanagement, miscommunication, or mishandling that goes into it. Our tunnel ventilation system is one of them. Out of 6, 7 things that can happen, tunnel ventilation system is one of them. And it is a chain of that event that can break that incident to become a disaster. And this is the reason we are all sitting here at this point, and we want to listen about tunnel ventilation system and how we can make it better, all those kind of things. So single critical event is never a disaster, for sure. During my presentation, please keep this thing in the back of your mind, that we'll be talking about only to break the chain of events so that an incident cannot become a disaster. It should not become a full-scale disaster. So what we have learned so far, this is very important. Maintain their, once in a disaster, people tend to maintain their roles and the work associated with their roles. Like if somebody is sitting there, he is looking at his mobile phone, he is least interested in knowing what is happening around. In this age, I think it's very, very pertinent. People don't really react to things very quickly. And until unless they are not able to see the actual incident that is happening. You might have actually, you may observe that there at one end there is a smoke event which is happening, and at the other end the people are silently sitting. They don't know whether there is a smoke event or not. It's very difficult for them to move until unless they see it themselves, and they are not in position to go there and see it themselves and witness it themselves. So very, very crucial movement of evacuations are getting lost, and we never rely on the information of passengers for any incident. This is the reason all the SCADA guys are doing whatever they can do to get the information themselves without any interface in between, because it's very unreliable. You cannot actually talk to public for getting an information on which you are going to be activating a life safety system. You don't do that. So therefore, people, in case there's an incident, people maintain their role, they don't react, they don't participate in the safeguards and all those kind of things. We, in our designs, we are not going to take their participation. We'll be designing our system in such a way that everything is visible to us, and we are in control of everything. The fire is at third coach, fire is at first coach, last seat, I should know it myself to take the corrective action myself. So this is what is the first point is, and of course fast and critical information, very clear, and the critical, if clear information is given, people generally react to it. Similarly, in case I want to move a lot of people, then people may not move because a civilian is saying something. They'll move when an authority is going to say something, when somebody in a dress is going to say something. These are some psychological aspects which, of course, we need as ventilation engineers, as safety experts, we need to know. And very interestingly, there's a behavior which is known as affiliative behavior. In case you want to evacuate people, or in case you want to take the people in dim light and with less clarity on where they have to go, they'll try to create some groups, small groups, this is known as what we termed it as affiliative behavior. In the affiliative behavior, if in that group there is a leader, in every group there is a small leader always, who is going to dictate the terms, and he is going to guide others to follow. If that leader is telling them something wrong, then everybody in that group is going to go wrong. So we need, as ventilation engineers, we need to ensure that there won't be any affiliation or affiliative behavior in our evacuation system design. We also learned ambiguity between major and minor accident. It's very important that we try and understand that what is a minor accident and what is a major accident, and when the minor accident can become a major accident. These are the clarity that we really need to train ourselves to understand. Tunnel gradient is one of the very important aspect. My colleagues in CMRL have discussed about gradients and all those kind of stuff, but you know that the smoke rises. In case there's a gradient, there's a natural direction towards which the smoke is going to flow. And there can be a possibility that the evacuation is in that direction. So we have to design our fans compensating that specific backflow. So maybe our fan parts are going to be slightly higher or something like that. Similarly, there are two ways to get to point of safety when you have two tunnels together. Then one of them is going to be your on the track evacuation, one is the other tunnel point of safety. These are the two ways that you can go. And sometime in our designs, in our earlier designs, we have observed that going from one tunnel to the other tunnel is hell of a task. I'll show you how it is. If can you run this video? Yeah, it's there, it's running. You see, we have done an experiment there in the Delhi Metro. Okay, fine. And I just want to, so you see quickly what happens. This is how you are going to evacuate. This is the worst thing that can happen in case you evacuate. These are all young people without heels. This is what they are doing. So this is something that we need to consider also in our design. And I'll talk about some dynamics of an emergency event as I discussed in the beginning. You receive an information, how do you react? You sometimes ignore or you sometimes investigate. Once you investigate, you can lead to three conclusions. Either instruct the others to agree to you, or you explore, or you withdraw. Then in case you instruct, somebody is not interested in your suggestion, he'll fight with you and he'll evacuate. You really don't have time to do all this thing in your design. You have to save lives. So our design must encompass all these understandings of human behavior during fire. Then these are various normal congestion and emergency operation modes that generally we design for in our systems. I'll not really go in detail in these things. I'll just focus on a couple of codal requirement internationally followed, which is EN 12101 and NFPA 130, as well as ISO 21927. All these codes gives some sort of overview how to design these things, how to ensure that our systems are working fine. And with respect to the ventilation system components, they have been listed in the beginning. So you have nozzles, you have fans, you have dampers, you have actuators. Let me skip that for a while. I'll give you a brief design overview here. And in this normal congestion and emergency scenarios, and of course the cold runs, which was discussed in the beginning, we calculate station's heat load, because for this room, the heat load is very fixed. For an underground section where say 800 kilowatt heater is moving here and there, the heat load varies with time. It's very dynamic, it's very transient. So how do you design your ventilation and air conditioning system? So one aspect is to understand what is the averaging of that heat load over a period of time, and that's how you put your heat load equipment or the air conditioning system in that. This is one of the part that is very, very complex, and it takes complex softwares to solve these things. One-dimensional airflow softwares or 3D airflow computational fluid dynamics. We also we are also interested in knowing temperatures on track when the trains are standing. We design for over track exhaust and under platform exhaust, if at all they are used. What is the size of these things? And then very interestingly, from which my career actually started, thanks to CMRL for that, is heat sink. Heat sink is that in an underground space, when you run your trains for say 40, 30 years, it's a it's a object with a lot of energy. It keeps on coming and going for next 40 years. It creates a kind of a heated environment within the tunnel. There is a capacity of the tunnel wall to absorb the heat. There's a capacity, you cannot go beyond it. In case the equilibrium is lost, then the temperature in the tunnel starts to rise. And this is one of the worst things that you would like to actually listen in any metro system. And for example, in London Tube, this is something that has been felt. It's a cold country, but still the tunnels are very hot, and they're doing something about it. Then effectiveness of piston effect induced in ventilation. This is something that we also look at. In congestion scenarios, stratified condenser temperature, correlation between stratified average temperatures. I'll come to that simulations in a while. Then pressure transients, etc. Emergency critical velocities, trackway exhaust, and evaluation of smoke backlayering in the tunnels. Now, let me be very clear in saying that you don't want to keep the tunnels in train in the tunnel. As soon as there's a fire incident about to happen or there's a smoke event, the first priority is to bring it to the trackway and deboard everybody, handle the situation. But in case that doesn't happen, the fire is still, the train is somehow, it doesn't have power or derailed or something like that, and then you have to handle the incident. For this event we are designing it for, just to break that specific chain that I was talking in the beginning. That's where it is. Then I'll talk about cold runs commissioning, and I'll try to answer that question, which is a very interesting question at that point. Now I'll come to very quickly the case studies that we really need to, how we do these things, how it looks to do these things. So starting from here, the heat sink is in any project based on its headway, based on the outdoor air climate, based on the how long is the train and everything else, based on the geological condition inside. When you start your operations, the earth temperature is something. But after 40 years, the earth has to absorb a lot of heat because of your operation inside in that tunnel. There is a specific limit on which you can run your train. You cannot run your train as you wish. I mean, it really is going to increase the temperature. So the headways and the stabilization of these things takes time, and it is something that needs to be evaluated. It is something that needs to be verified. So for say for Mumbai Metro, the stabilization, the heat transfer rate, what is coming out and what is going in, it takes around 7 years to stabilize. For first 7 years, the tunnel temperatures are going to keep on rising on an average. Similarly for Chennai, it is a 15-year number, something like that. Then eventually it is all about fans. I need to know if a fan is responding to a certain situation with a certain duty point, then whether I'm putting my fan, I'm procuring my fan and I'm putting it to the situation, whether it is going to address that situation or not, these kind of testings are going to help me handle that. And you can see it's a CFD model wherein we are able to understand complete supply and the exhaust and the use of nozzle and the silencer and everything. We can point out what kind of pressure drop, what kind of velocities, what kind of noise, and all those kind of things are coming. And we can actually put all these things on these fan curves, which are given to us by various vendors. Then this is with respect to fire and smoke dynamics in the tunnel, with respect to when you run the fan longitudinally from one side and extract from the other side, how the back layering happens. Let's see. This is the video which is running right now. It's going to take a bit of time, so let me just leave it. You can push it. This one. This is the evacuation. This is the other one. These tunnel ones. Or maybe leave this thing for a while. I'll speak about critical velocity. So critical velocity is the velocity which we were discussing about. I mean, that's the minimum velocity which is required to ensure that the smoke doesn't come towards the side of evacuation. And here is some of the different codes and different megawatts. What are the velocities that we eventually have to design it for? So you can see, if I design it for say 3.5 meters per second, then I'm safe in most of the code. As far as most of the codes are concerned, if I design it for 3 to 3.5 meters per second, I can handle 20 megawatt of fire. So there is always a debate that my fire load is 20 megawatt, your fire load is 10 megawatt, you are not designing it right or something like that. As and when the fire load grows beyond 25 megawatt, there is a little change in the critical velocities requirements. Then this is with respect to pressure transient. This is how when the train goes in the tube, it generates a small pressure wave, and that pressure wave can be harmful to the equipments in the tunnel, and it is also sometimes uncomfortable because it creates a kind of sensation in the ear, oral comfort. So we mimic that situation in the simulation model with respect to what is the speed, what is the frontal drag coefficient and everything within the simulation model, and we understand what kind of pressures are going to rise in how much time. And there are certain compliances for that. This is with respect to congestion. Your air conditioning, your coaches are air conditioned, and you never felt that the coaches are not working, their air condition is not working. But imagine a situation that the train is stuck for say 10 minutes or 15 minutes in the tunnel. Your air conditioning system, by the virtue of its design, is to reject the heat, inside heat to the outside. And in case the outside temperature goes beyond say 60 degrees centigrade, 65 degrees centigrade, your air conditioning system is going to fail. Am I right? So what you do, you design your ventilation system to ensure that the tunnel temperature doesn't go beyond a certain point, and as soon as this congestion situation comes up, you supply your ventilation system. This graph basically shows that in case the temperatures are reaching to a kind of to initial temperature 36, in case you keep on running these air conditioning units without ventilation system, their performance is going to degrade to 50%. Okay. Then this left graph that you see here, this one, in this one you will see that within 60 seconds, the performance, as soon as the temperature starts to rise, the performance of the condenser in kilowatt comes down. So we design it for our ventilation system is designed for such kind of handling such kind of situations. We also verify in case you're using a booster fan or jet fan in cross passages, just to ensure that you want to send the air on this side, whether it is going on that side or not. So in the simulation model using computational fluid dynamics, we can assess the performance and the efficacy of that jet fan. Similarly, trackway exhaust system. Trackway exhaust system, you have just where the train docks on the station, there is a duct on the top, and that duct takes away the heat. That duct, in case that duct is just beneath, the duct's openings are just beneath the condenser, which we design it for, it takes away almost 70% of the heat. In case the train stops slightly offset to that specific position, you have 48% of heat rejection, 43% of heat rejection. So this is something that we all know about, and this is how we design, and this is how we interface with the signaling, where to stop the train, where not to stop the train. Then a very important component of our ventilation system design is nozzles. Because nozzles supply, they add momentum in this duct or the entire tunnel, and which is extracted from the other side. And I'll address this specific question of that at that point. He was saying supplying less and taking out more is a good idea. Yeah, it's a very good idea, and we do it. What happens when you supply from the nozzles, it adds the momentum. The overall flow that goes into the tunnel, you're supplying 85 cms from the nozzle into the tunnel. It is only going inside as a total, if you are supplying 85, the entire tunnel might be receiving only 40 cms. Because you are just adding the momentum. Okay, and then you are extracting there from the other end 85 cms. So you are effectively supplying less and taking out more already. And this actually covers your density differential, because in this pipe, you are adding heat at a point, you are expanding a lot of air. And that expansion of air is scattered in this situation. And in case you supply the same amount which you are whatever you are extracting, then what would happen is that it would be an overshooting condition. The smoke is going to go to the other next station. We don't want to do that. Therefore, we always extract more and supply less. And the current system that we build, they are inherently doing that only. Yeah. Then, so this is with respect to the nozzle, how we design the nozzle. And sometimes how a specific mode of operation in normal mode is going to behave or is going to react to the annual tunnel comfort. This is how we can confirm and we can model. We can also do thermal comfort modeling within the tunnel environment in case it is not air conditioned through various 1D and 3D softwares. This is an example of that. What you see here in this one is an IDA tunnel model. And this is a very specific video with respect to tunnel cooling. You guys have already talked about it. Let me just run it for a while. You can see As soon as the train arrives, the system is going to heat it. This is, the train is arriving and the shaft is taking out the air and then it is coming back. This is how the air moves through the system for a specific situation. You see this, outside air coming in, and there is a cooling dumping mechanism here that is sending the cooling inside. So effectively, all these phenomena, they are all governed by some mathematical physical equations. So you combine all these things together, you find out the right software, and then you correlate it and model it here in this one. Now I'll come very quickly to the tunnel ventilation requirement as far as, the station ventilation, station CFD requirement. So you see this is a station, and in this station what you will see here is that so this is a plan view of the situation, and in between, in the middle, you have a fire there. How the smoke at 1.2 meter height is going to be there, this is what you check here in this one. 2.0 meter height, the human height, average human height. This is a section, how the smoke spreads in these specific floors. This is what it is determining here. And what we are doing is, we are calculating available safe egress time and required safe egress time. There is a time to which the smoke, there is a time which the smoke takes to come down to this head height. And during that time, you have to evacuate everybody. This is a asset and reset, available safe egress time and required safe egress time. Then let me go to the next one. This is again an example. This is a coupled asset and RSET CFD simulation. You can consider that to be an advancement now. This is a 4-level station, and in this 4-level station, during an emergency, here is the fire. And this is a 2-meter plane that you see. And people are also moving out. So what we are doing is, we are calculating what dose every agent, every individual has taken. And if that dose is beyond the dose of FED, fractional effective dose, then there would be a problem. Okay, so these are coupled airflow, coupled CFD and evacuation simulations. Then I'll wind up just by showing you another slide which is of interest of the civil people. I think, let me just skip this part. No, not this one, sorry. I just want to show you about the commissioning first. So this is what it takes. This is how it works. For people, fan starts, all smoke going one side. And then you have these kind of checklists. You put up all these things, you ensure that every system is the way you have anticipated them to work, and then you check whether the system is able to, bring you the velocities or not. So it's a physical verification. And one more thing, I think it came up during the last discussion. It was with respect to cold runs. And cold runs are basically how the cold runs are associated with this. What we do is, whenever you can't measure a thing, I mean, when in the earlier times you didn't have a feet length established, you have a reference at least. Now you have scales. We have scales, but earlier we don't have a scale. Similarly, in the complex physical systems, when you cannot measure something effectively, you take helps of calibrated models. Am I right? Am I making sense? Calibration means that you effectively handle one part of the model, which is, say, without heat addition. And if it works well, your heat addition part is also going to work well. This is the law of physics. This is law of scaling. We call it model-based design. So this is exactly what we do in cold runs. We run the model with fire. We ensure that everything is working fine as far as the fire growth and the density differential is concerned. And then we switch off the fire in the model. Run it as it is. Whatever velocities are coming by then in those ambient temperatures, we ensure that those velocities are met in our real design. This is what a cold run is all about. It is not that complex, but yes, it requires a bit of understanding and the way model-based designs are working. Then, sorry, get this one. So this is a very quick overview of how we model 1D. It's a snapshot of IDA tunnel, wherein you can see various components of the tunnel, various fans, cranes. So all of them are modeled simultaneously in a single modeling environment. You can even model controls also, that as soon as the opacity goes beyond this particular point, I need to run my fan from this direction, that direction. Similarly, or maybe I need to do a kind of a PID controller to ensure a velocity of 3.0 meters per second. So this is in a single environment. So when you model everything in a single environment, what it gives you is that any aspect, any chain of event that in the beginning I discussed about, if something is missing, you'll catch it here. And this is what is all about verification and validation of the system and the designing as well. Then, so interface with SCADA, interface with the designs that we do is very important as far as SCADA is concerned. Our interface with civil is also very important in evacuation planning and evacuation management. I'll show you this thing in this one. This is a very typical work that we have done just by swiping the staircases from one side to the other side. What is the impact? This is going to give you that. This is here you see the staircase and escalators are swapped in that one. What I'm saying is that you can see the impact just by a decision. It depends on from where the people are originating in an underground environment. So I would like to highlight that this interface with civil is lacking. We don't interface with civil that much, that the way we have to, as far as tunnel ventilation engineers. We need to be a part of their evacuation planning. With this, I would like to extend my great regards to CMRL and ISHRE. Thank you very much.